So first of all, let me introduce what is the classical model of computing that we're going to compare with the quantum analog model of computing. So we're going to talk about classical query algorithms, and in classical query complexity, we are given a Boolean function defined on a subset of the Boolean cube that is known. So we're going to know that function, and the goal is going to try to compute the function on an unknown input. Meaning that this input is going to be hidden from us. You can imagine that someone else knows the input, and what we can do is just access parts of the input, because maybe accessing some part of the input is very costly. So the way that you can imagine this is that what you can do is ask some questions to the person that hides the input from us. So you can make some queries, and by a query we mean a question where we ask for an entry of the input, and then the person that knows the input, which knows the full input, replies with the value of the input on that entry. So you can imagine this as applying this oracle map that maps the numbers from 1 to the n to the corresponding entries of the input. Okay, so what we are going to do is to try to design a strategy to ask these questions such that with few questions, with few queries, we can compute the value of the function. And this is somehow a definition, but maybe it's also useful to talk about an example. So what I kind of claim is that decision trees encode classical query algorithms, and I want to prove that somehow this decision tree, which has depth 3 and then is going to make 3 queries, computes this Boolean function that has 4 variables. So somehow this is not trivial, because something trivial that you can always do is ask for the whole input, which has length 4 in this case, and just get out the value of the function, which you know. So we are going to show that with only 3 queries we can compute this function. So I need a volunteer that thinks of 4 bits, and then I can test that the decision tree really works. So any volunteer that is just thinking, okay? So what I'm going to do is first ask you what is the value of the first entry of your input. x1, what is the value of x1? 1. Okay, so the way that you should treat a decision tree as a classical query algorithm is first you ask for x1, and then you go where the value 1 is. So it goes to a node with the label of x2. So now I'm going to ask you, what is x2? Minus 1. Then I go here, I ask you about x4, and what? Minus 1. Then I say that the value is minus 1. Okay? So let's see if we are correct. So what we did was going here and here. So x1 it differs from x2. So this is going to be 0. Okay? And here we are going to have x1, which is 1, minus x2, which is minus 1. So this is going to be 1, and we are just going to output the value of x4. And that is what we did. So x1 was minus 1, and then you get minus 1. And you can check that this is an algorithm that makes only 3 queries and computes this function that has 4 inputs. So you can do non-trivial things. And this is how you can think of classical algorithms. It's not very important for this talk, but for the people that are not familiar with computer science, maybe it's nice to have an idea of what are the objects that we are going to care about. And of course, in general, the goal is to try to design an algorithm that succeeds on every element of the domain using few queries. And the minimum number of, before saying that, I want to say that we are also going to allow the algorithm to make random decisions, meaning that in between can toss coins. And we are going to ask the algorithm to be correct with high probability and not always, like just with 99% of probability. So if we of course, the task is going to be to try to use the minimum queries, and the minimum number of queries in order to solve this task is going to be denoted by the classical query complexity, which is denoted by CF. So this is the classical word, and Aaronson-Ambainis is a conjecture about comparing classical and quantum query algorithms. So first of all, I need to tell you very briefly what is quantum computing. So this is going to be very simple. And I'm just going to be I'm going to give a very brief introduction to quantum computing, which is enough to kind of understand quantum algorithm in this setting, but is definitely not enough to describe all quantum algorithms. But if you don't know anything about quantum, maybe you should think that when you have a quantum system, which is just a system of particles that are very small, very tiny, and have different laws of physics that describe the system, then those systems are described by states which are unit vectors of some complex space. And the legal operations are going to be those that carry states to states, meaning that they are going to be those that carry unit vectors to unit vectors, so they are going to be unitaries. And sadly, when you have a quantum system, you cannot get all the information about the system, meaning that you cannot get a full description of the vector that describes the state. Instead, what you can do is measuring. And when you measure, what you are going to do mathematically is the following. So you are going to take the state, you are going to look at it as a vector that can be written a linear combination of the elements of some canonical basis, and what you are going to do when you measure is going to sample from the probability distribution defined by the squares of the coefficients. So this is a probability distribution because it's a unit vector, and what you are going to do is sampling a label I according to this probability distribution. So this is somehow a very rough idea of how quantum algorithms work, but I hope that that is enough to understand quantum query algorithms.
And D is M?
Excuse me?
D is equal to M, or D is different?
Oh yeah, this should be M.
Okay.
Yeah, that's a typo. Okay, and this is what we have. I don't know if there is other questions. Okay, good. So we can continue, and again, in quantum query complexity, the problem is the same. You are given a full description of a Boolean function, and now you have to be able to compute the Boolean function on a known input without asking too much about the input. But now the way that you can ask about the input is by a quantum queries, which now are going to be given not by an oracle map that maps numbers to plus minus ones, but instead they are going to be unitaries, because those are the legal operations in quantum computing, and are going to be unitaries that map the elements of a canonical basis to the corresponding element times the corresponding entry of the input. So you can think of the oracle map of the quantum query as a diagonal matrix that has the entries of the input on the diagonal. So that is a way that a quantum query algorithm accesses the information about the input, and how does a quantum query algorithm look like. So we are going to start with a fixed state, which is somehow making the first decision, like in this case, in the decision tree case, to say that the first question that you're going to make is x1. So it's like the first decision that you make even before making a query. So after that, you are going to make a query, and then you can do another query. But before that, you can do some computation in between queries. This computation should not depend on the input because you don't know the input. So it must be an independent unitary that is independent of the input. And you can repeat this, let's say, d times, and you're going to end up with a state that has some information about the input. And now we want to get some output plus or minus 1 out of this. So what we can do, as I said, is measuring in the state, which means that we are going to sample from this distribution, and depending on the outcome I, we're going to output 1 or minus 1. And what we want is that this outcome corresponds to fx with high probability. So this is how a quantum algorithm looks like. And again, the goal is to design an algorithm that with 99% of probability computes the function, and the minimum number of queries to perform this task is QF. So it's the quantum query complexity. Is this clear, or maybe not clear, but like maybe you already have a feeling of what is going on? Okay, I guess so. So now the question is, how do these complexities compare? So we know that quantum is at least as powerful as classical. So this means that the classical query complexity is always at least the quantum query complexity. So that is good news. So this means that maybe quantum computers can be useful. This is not enough because we want like somehow quantitative separation between both of them. And we know them. So we know an example of a very structured problem, a very structured sequence of Boolean functions such that the classical and quantum query complexities are very different. What do I mean by structure? So what I mean by structure is that the domain of the function is very small with respect to the size of the Boolean cube. And why is that being a structure? Because somehow when you get an input, you know that you're, as an algorithm, when you get an input, you know that the input is going to be an element of the cube, but you also know that it's going to be an element of the domain. So if you know that the domain is very small, you know that the input that you're going to get is not a random element of the Boolean cube, but it's a very special one, it's a very structured one, because it belongs to the domain that is very small. So there is a sequence of Boolean functions whose domain is very small that witness an exponential separation between classical and quantum query complexity. So usually what you are said when maybe you have heard at some point, even if you don't do math, even if you don't do quantum computing, sorry, that classical algorithms can be exponentially outperformed by quantum algorithms. What we usually mean is that in some kind of query model, we have exponential separation like this. So this is what we mean by having a quantum speedup. Right? So this is a setting for problems that are very structured, but in the opposite setting where you have no structure, meaning that the function is defined on the whole Boolean cube, there is no separation that is exponential. So what we know is that for every Boolean function that is defined on the whole Boolean cube, the classical query complexity is at most the fourth power of the quantum query complexity. So in this setting, we cannot achieve speedups that are super polynomial. Okay? So the question that is open is what happens in between. What happens if you know that your Boolean function is, say, defined on a big part of 99% of the whole Boolean cube, but still is not the whole Boolean cube, so you cannot use the analysis tools that you need to prove this. So in this setting, what we hope is that to find some quantum speedup. So the community has tried a lot to find exponential quantum speedups in this setting, but we have not really succeeded. So the conjecture is that in this setting, there is not a real exponential quantum speedup. So that is a conjecture. We believe that in this setting, there is no exponential quantum speedup. So this means that we need a structure to obtain exponential quantum speedup. So the big conjecture in quantum computing that is unproven so far is that to obtain exponential quantum speedups, you need a structure. Okay? Yeah, I don't know if there is any questions.
Do we know, is that tagged to the Q to the 4? Is that known?
Yeah, no, I don't think it's tagged.
It's not tagged.
I don't think so. Yeah, I don't remember. Like there is, I guess, like there is this paper by like that was a follow-up work to the sensitivity conjecture, where you can find this table with comparisons of all the complexity measures of Boolean functions for total Boolean functions, and then you can go and see what is the row and column corresponding to these two. But I think it's not tagged. What?
The deterministic query complexity is tight. Like the paper of Ambainis develops another.
Oh, we know that it's tight.
Yeah, for deterministic query complexity on the left-hand side.
For the deterministic, okay, but I'm talking about randomized here. Like I'm using the notation of deterministic because I wanted to use C to say classical because maybe I think it was easier, but yeah, this is not deterministic. So I think that this is open, right?
I think maybe then.
Yeah. So, yeah, so like this is somehow the motivation, like to try to understand what is the separation of quantum and classical query algorithms in this setting where you have that the domain is the 19% of the Boolean cube, and the conjecture is that we need a structure, meaning that in this setting we cannot find quantum speedups, and the way that people usually phrase this conjecture is this way, is that every D-query quantum algorithm can be simulated on 99% of the input by a classical algorithm that makes Fourier queries. So maybe this doesn't look like saying that quantum speedups need a structure in order to be super exponential, but indeed it does. And to explain why, we are going to use this picture. So let's try to consider a problem where the domain of the function is very big, meaning that it's a big chunk of the whole Boolean cube. Then, if we believe this conjecture, whatever a quantum algorithm does can be simulated on a big chunk of the Boolean cube, also here, 99%, and the intersection of two sets that are 99% of the measure of the whole Boolean cube is going to be very big, it's going to be 98%, so somehow what happens is that if we have that the domain is very big, and if we believe this conjecture, then we are going to have that we can simulate with a classical algorithm, only polynomial set, whatever a quantum algorithm does to compute this function. Okay? So somehow what we want to understand now is this conjecture. Is this conjecture true or not? So that is somehow the question. And now, I guess that some of you are not familiar with quantum computing or even with computer science, so maybe this was just some motivation, but it was like not appealing to your taste. But from now on, what we are going to do is just forget about quantum, and we are just going to talk about polynomials. And we are going to talk about analysis in the Boolean cube. And we can do that because of a result that is more than 20 years old and says that quantum algorithms are polynomials, meaning that every equal quantum algorithm can be captured by a polynomial that has degree at most 2D and is bounded on the infinity norm by 1. So what do I mean by the quantum algorithm being captured by a polynomial? So what I mean is that, okay, let's pick a quantum algorithm. What we are going to, we should realize that at the end, a quantum algorithm on every input is going to output 1 with some probability and minus 1 with other probability. So for every x, the quantum algorithm is essentially a random variable, this binary random variable, right? So if you want to understand a binary random variable, you just need to understand one parameter, either the probability of 1 or probability of minus 1. You can also just understand the bias of the difference between the probability of measuring 1 and probability of measuring minus 1. So what I mean by the fact that a quantum algorithm is a polynomial is that the bias of the quantum algorithm towards 1 is a polynomial that has some restriction on the degree that comes from the number of queries that the algorithm makes and is bounded on the infinity norm. So this is a way of forgetting about quantum algorithms, and if you can say something about quantum algorithms, then you can, if you can say something about polynomials of this kind, then you can say something of quantum algorithms. So in particular, let's go back to the question that we cared about. So we cared about this question that says that we want to show that we can simulate quantum algorithms with classical queries. So then what we can do is to, given a quantum algorithm that makes the queries, pick the polynomial of degree at most 2D and infinity norm at most 1, and we want to evaluate that polynomial on a known input without knowing too many entries of the input. So if we can do that, then we can simulate quantum algorithms, okay? And if we can do that in a classical way, meaning that we can somehow ask for few entries of the input to the oracle, get some information about the entries of the input, and then output something that is close to this polynomial. So that is going to be the strategy, and that was the idea that Aaronson-Ambainis had in mind when they proposed the conjecture that we are going to see in the next slide. But before doing that, what we are going to do is to sketch the proof of this fact, which is kind of simple. So recall that the quantum algorithm at the end, what did was preparing a state like this. And remember that this OX is just a diagonal matrix that has the entries of the input on the diagonal. So when you multiply all these matrices, as we have D times the OX, the entries of the matrix here is just going to be a matrix whose entries are going to be polynomials of degree D. So at the end, the coefficients of this vector of this state are just going to be polynomials of degree D. So the squares of the coefficients are going to be polynomials of degree 2D. Then at the end, remember that the probability of measuring 1 was just the probability of, like what we did was just at the end of the quantum algorithm, what we did was measuring, which means that we sample from here, and depending on the label I that we output, we say that the value of the function is 1 or minus 1. So the probability that the algorithm says that the value of the function is 1 is just a linear sum of these guys, and the same for minus 1. So the probability of measuring plus or minus 1 is just a sum of these squares of the coefficients. So these probabilities are going to be polynomials of degree 2D, and thus the bias is going to be a polynomial of degree 2D. And as the bias is the bias of a random variable, is going to be between 1 and minus 1. So we have this because of the structure of quantum algorithms, and we have this just because it's a bias. Okay, so is everything clear so far? Okay.
What does it mean, the probability of being plus or minus 1? It's always plus or minus 1, right?
Yeah, I was abusing notation, so I say that the probability of AX being 1 is a sum of these guys, and the probability of AX being minus 1 is a sum of these guys. I just didn't want to write two lines. So like you can interpret this, the probability of outputting 1 is a sum of these squares, and the probability of output minus 1 is a sum of those squares. Okay. So, okay, I hope that this is clear now, and from now on, you can zoom in again if you didn't like the quantum part. Now we are just going to talk about polynomials, and what we are going to do is going to talk about the Aaronson-Ambainis conjecture. So Aaronson-Ambainis had this idea of, okay, if I can say something about polynomials, then I can say something about quantum algorithms, and in particular, if I can say something of evaluating polynomials on an unknown input without knowing too many entries of the input, I can say something about simulating quantum algorithms with classical queries. So to say something about this problem, what Aaronson-Ambainis conjecture was that for every polynomial defined on the Boolean cube with infinity at most 1 and degree at most d, the maximum influence is at least polynomially big with respect to the variance and the inverse of the degree. So let me introduce a bit of notation. So here we are going to look at functions defined in the cube as polynomials that are multilinear, and we are going to look at this expansion, which is the Fourier expansion, and there is other two elements that appear here, which is the variance, which is defined like this, and it has a convenient expression in terms of the Fourier coefficients as the sum of the non-empty Fourier coefficients, and we are also going to consider the influence, which is a measure of how relevant a variable is for the polynomial, and is expressed also in terms of the elements, in terms of the Fourier coefficients as the sum of the squares of the Fourier coefficients, and the maximum influence is just the maximum of the influences. So with these definitions in mind, what Aaronson-Ambainis conjecture is somehow saying is that for the polynomials of the kind of the polynomial method, what we have is that for them there is always a very influential variable, that there is a variable that is responsible for a big part of the variance of the polynomial. So why this is somehow going to imply that it's true that quantum speedups need a structure. So I claim that if we want to simulate a quantum algorithm that makes the queries, then what we just have to do is to evaluate a polynomial of degree at most 2d that is bounded on the infinity norm on some hidden input without knowing too many entries of the input. So this is thanks to the polynomial method. So now we are going to just focus on this, and how can we show that this is true if the Aaronson-Ambainis conjecture is true? Well, they propose Aaronson-Ambainis in that paper a way of evaluating the polynomial by making a very small error almost everywhere, and this way was somehow the natural that you could expect after seeing this conjecture, which is first, I don't know anything about the input, okay? So what makes more sense is to query the most influential variable, because that is the most relevant variable for the polynomial. So I just pick P, I take I1, the most influential variable of P, and I just query the polynomial on whatever value of xi1, I restrict the polynomial to whatever value xi1 or the person that knows the hidden input has told me that is the value. Okay, and I then restrict P and I get P1, and what happens is that you are going to get a polynomial with one less variable, but this is still going to be of degree at most 2d, and it's still going to be bounded on the infinity norm. So it still is going to have a very influential variable. So I call it that influential variable. Okay? And again, I restrict the P1 to whatever the most influential variable gets as value, and I get P2, and I repeat this process a few times, and at the end, what is going to happen is that we will have queried a few influential variables, and as they are very influential, the remaining ones are going to be not very influential, because we will have decreased the variance quite a bit. So at the end, what is going to happen is that we are going to end up with a polynomial after restricting in this way that has very low variance. So the expectation is going to be a very good approximation of the value of the polynomial almost everywhere. So what we are just going to output as the value of the polynomial is the expectation of the polynomial when you do these few restrictions of the polynomial. So if Aaronson-Ambainis conjecture is true, then we just need a polynomial number of a poly number of iterations of this process of query restriction. Okay? So is this clear? Is it clear that Aaronson-Ambainis would imply that you can simulate quantum algorithms with only polynomial head? Okay. So now what I want to say is, what do we know about Aaronson-Ambainis conjecture? And if I want to give a short answer, it would be we know very little. Like, we are very far as a community from proving it. But there has been like quite a few efforts to try to say something, and like even saying something partial or reducing the Aaronson-Ambainis conjecture to other kind of problem is interesting, because somehow we don't know how to attack this basically looking at fundamental problem in computer science, that is also a math problem, as it is phrased just in terms of Fourier analysis. And we know some things. So in fact, the Aaronson-Ambainis conjecture was not a conjecture that came out of anywhere. So what Aaronson-Ambainis were inspired by was this paper of Binur Friedrich and O'Donnell of 2007, that is very famous. And in this paper, what they showed is something that had one corollary, and the corollary was that the maximum influence of a polynomial of degree at most d is at least a polynomial depending on, here I should say poly, sorry, a polynomial is polynomialic with respect to the variance and the inverse of the exponential of the degree. So somehow this is a weaker version of the Aaronson-Ambainis conjecture. If we manage to change here 2d by just d, then we would have 1. So Aaronson-Ambainis said, okay, we have this corollary of this DFKO theorem. Maybe we can improve the corollary if we just focus on the corollary from exponential to polynomial. So that was the inspiration of Aaronson and Ambainis, and this weaker version of the Aaronson-Ambainis conjecture also follows from other work of the Fama, Steele, and Perez. So this work, the Fama, Steele, and Perez, what they were doing was proving the Boolean-Euler inequality for polynomials defined on the Boolean cube, and they gave a nice proof that obtained a good constant, and they could also use this proof to recover this weaker version of the Aaronson-Ambainis conjecture.
So does it mean in this language that we can get what they want by classical algorithm, but not in the poly d, but in exponential d?
Indeed. So you can simulate, this implies that you can simulate a quantum algorithm that makes the queries with xt classical queries.
And this proof that D here is not coming from the polynomial constant. Even
No.
if we're decoding the constant, it will still be exponential.
No. So like, I don't think that there is a proof that says that Boolean-Euler implies Aaronson-Ambainis. I suspect that that might be the case, but we don't have any proof. I have tried a bit and I don't really see how. But what happens is that there is a common proof somehow that, like essentially the same proof strategy that they use to prove that the Boolean-Euler constant is sub-exponential, like they saw that is x to the square root d. Then if you just take some part of the proof, you get Aaronson-Ambainis with 2 to the d. But it's somehow, like, it's not Boolean-Euler implies Aaronson-Ambainis, it's that somehow in some cases there is kind of a common proof.
But even, I mean, if one were to completely optimize the proof, get constants everywhere, do you know what it would give for Aaronson-Ambainis?
What do you mean?
So if the common proof that you're talking about, if there's no dependence on D there, as we would do it for BH or something.
So
Yeah.
there's a new proof of BH so that the constant is 7 or something.
Yeah, but that's this proof. Not
It
this.
has to be, yeah.
No, I don't think like this common proof could not achieve better than exponential, I would say.
Okay.
Like there is a common proof of for both Boolean-Euler and Aaronson-Ambainis, but we know that that common proof will not be optimal for Boolean-Euler. So this is some weaker versions. And we also know particular cases. The first one was for Boolean functions, so this was even known before the Aaronson-Ambainis paper. So it was the OSSS inequality that is also very famous, and essentially says that this Aaronson-Ambainis conjecture is true for Boolean functions. So we care about bounded polynomials, but for Boolean functions we know that is true. And there is also a blog post by Patrick Benisvili where he shows that it's true for symmetric functions. And Montanaro, in a paper where he took some hypercontractive inequalities and found very nice applications in quantum computing. Something that he did was taking the polynomial inequality for multilinear forms and showing that for these multilinear forms, the Aaronson-Ambainis conjecture is true. So again, we see a connection between Aaronson-Ambainis and Aaronson-Ambainis, but I stress that it's not. I don't know any proof of one result implying the other or vice versa. But in this case, what Montanaro did was taking multilinear forms, which are polynomials, where you can divide the variables in deep blocks, and in every of the monomials of the support, you can find one and only one variable from every block. So it means that with respect to every block, these forms are linear, so that's what we call multilinear forms. So if you pick multilinear forms whose coefficients are plus or minus ones, then Montanaro showed that in this case, Aaronson-Ambainis conjecture is true. So this is a narrow case, but this is still some case where we can say something.
So it's not really a polynomial if we think of Montanaro. It's not really a polynomial. It's like a form. Right?
It's a form, yeah.
It's a form.
Yeah. Like depends on who you ask. Like this very restricted class of polynomials that is way more structured. So yeah. So in this case, you could just say, okay, for this kind of forms, like the influences and the variance are very easy to compute, and you also can say something non-trivial about the infinity norm and the norm of the coefficients of this polynomial by using monomial square inequality, and things work in this case. So these are the particular cases that we know. We also know that it can be reduced to other conjectures that maybe are also hard, like we have not been able to prove any of these conjectures either, or particular cases. I think like there is not much progress on these lines. So what I want to mention is that it suffices to prove for one block decoupled polynomial. So these polynomials are polynomials where you have two blocks of variables, and for one of the blocks, that block is decoupled, meaning that it acts like if it was in a multilinear form. Meaning that for every monomial of the expansion, there is only one variable of this block. So it's somehow having one special block that resembles the behavior of the multilinear forms. So for this kind of polynomials, Aaronson showed that it would suffice to prove the conjecture for this kind of polynomials, which is a nice progress, but still we have not been able to say much about this kind of one block decoupled polynomials. There is also other reduction by Loget and Sang that says that there is two conjectures in fractional certificate complexity, whatever that means, that if proven would imply Aaronson-Ambainis, and there is a recent work by Bhattacharya, I think maybe I'm mispronouncing the name, that says that Aaronson-Ambainis conjecture is true for random restrictions. I think that there is also another recent paper claiming that they have proven a similar statement, not comparable with the one of Bhattacharya, that also says that Aaronson-Ambainis conjecture is true for random restrictions, but not comparable. So this is somehow what we know about Aaronson-Ambainis. I also want to say that there is some connection to cryptography. I think that if Aaronson-Ambainis conjecture is true, there is like some implications in cryptography, but I'm not very. I tried to read the paper, but I cannot really grasp the meaning of Aaronson-Ambainis in that context. And this is what we know, but we also know something else. And the other work I want to highlight is that we have a weaker but meaningful version that was by a work of Van Salsing and de Wolf that says that Aaronson-Ambainis conjecture is true for completely bounded block multilinear polynomials. So somehow this says that if you change the infinity norm by another norm that is the completely bounded norm which is the norm that you would get when you, instead of taking the supremum of the polynomial over scalars, you take the supremum of the polynomial over matrices that are bounded. Then, if you change the infinity norm by the completely bounded norm, you can prove the Aaronson-Ambainis conjecture in some restricted case where you have the extra algebraic structure that the polynomial is block multilinear. That is somehow a non-homogeneous generalization of multilinear forms. So I'm not going to talk about the details of this, but what I can say is that it's going to be similar but not comparable to what I'm going to present in the second half, which is an approach towards Aaronson-Ambainis conjecture via Fourier completely bounded polynomials. So you can even see that the name of the norm is similar. But yeah, so this was somehow a previous work, my work is a follow-up work to this one, and these kind of polynomials are still relevant because, as we are going to see, quantum algorithms not only output polynomials that are bounded on the infinity norm, but they are completely bounded in some sense. Okay, so this is somehow the overview of what we know about Aaronson-Ambainis conjecture, and I guess that I have convinced you with these many partial research that has been this is the work of the community during 15 years, so I guess that I have convinced you that Aaronson-Ambainis conjecture is hard. I hope that at this point somehow everyone believes that. So maybe we don't have to prove it. So the real reason that we care about Aaronson-Ambainis conjecture is that we want to understand the separation between classical and quantum query algorithms in this regime when you don't have much structure. But as we are going to see, that Aaronson-Ambainis conjecture is not needed for that purpose. And why is that? That is because the polynomial method can be refined. So we know that every quantum query algorithm outputs a polynomial like this, but it's not true that every polynomial like this comes from a quantum query algorithm. So here there is some polynomials that might not come from quantum query algorithms, so maybe we should not care about them if what we care about is the Aaronson-Ambainis conjecture. And we know that if we change the infinity norm by the Fourier completely bounded 2D norm, which I'm going to introduce in the second part of the talk, then we have a type characterization, meaning that every polynomial with this kind comes from a quantum query algorithm, and every quantum query algorithm gives you a polynomial of this kind. So these are the class of polynomials that we should care about. And I'm going to introduce this norm in the second half of the talk because it's kind of technical, and we are going to do some proofs using that the definition of this talk, of this norm. But for the moment, what you should think is that what I said, that the infinity norm is the supremum of the evaluations of the polynomial on Boolean strings, and you should think of the Fourier completely bounded norm as the evaluation of the polynomial on matrices that behave like Boolean strings. So we are going to define with precision what is behaving like Boolean strings in the second part of the talk, but for the moment, just think that the infinity norm can be relaxed, allowing also more elements on the input that on the supremum that are matrices that behave like Boolean strings. So, and of course, the Fourier completely bounded norm is going to be bigger or equal than the infinity norm because we are going to extend the place where you can evaluate the polynomial in your supremum. So here, when I say evaluating the polynomial on matrices, I mean matrices of any dimension that behave like Boolean strings, but of any dimension, in particular of dimension 1. So the Fourier completely bounded norm is going to be strictly, well, it's going to be bigger or equal than infinity. So that is some intuition that you can get for the moment.
But is it, I missed, is it clear that the thing which appears from quantum outputs has this property that completely bounded norm will be less than full than 1?
No, it's not clear. Like this was it's not clear. So I think like this
it's
was
just a particular case, right?
No. In general, this is true. Like
It's always true?
It's always true. But like it's not clear how to see that. Like in fact, like we knew the polynomial method is a result. The fact that quantum algorithm output polynomials that are bounded on the infinity norm about the degree. This is something that we have known for more than 25 years. But this is very recent. This is something that was only discovered recently, and somehow it was an open question that had been around in the mind of the community for a long time, like to try to give a meaningful notion of polynomial degree that characterizes quantum algorithms. But this was only recent, and this was not so easy to know because somehow this required a result from another area, which is what I'm going to say now, which is the Christensen and Sinclair factorization theorem, which is just a result of operator spaces. So maybe some people working on functional analysis have heard of this, maybe not, because it's pretty particular to operator spaces. But there is a big result behind this, and this is the Christensen-Sinclair factorization theorem. So we took a while to really prove this refinement of the polynomial method because there was a result of other area that we needed to use. And this was done, in fact, by Srinivas and Arunachalam, Joe Priet and Carlos Palazuelos in 2017. So they were the ones that first gave a tech characterization of quantum algorithms in terms of some notion of polynomial degree. What they did was essentially this, but I'm going to talk about the Fourier completely bounded 2D norm, which is somehow another presentation of the result. So so they gave here the same norm but with a different expression, and the way that, so the norm that I'm going to present has a Fourier analytic flavor, which I think that is amenable to work with, and they didn't give that presentation, and what I did to get like this presentation was like taking a follow-up work by Sandra Glibrin and Monique Laurent, who took the completely bounded norm that Srini and friends use and showed that completely bounded norm is a semi-definite program. For those of you that don't know what is a semi-definite program, it's just a linear program where you can also have some extra restrictions that say that certain matrices are positive semi-definite. It's not very important, but like Glibrin and Laurent showed that somehow the norm that was appearing here in the original version of the result by Srini and friends can be phrased as a semi-definite program. Then looking at the dual of that semi-definite program and doing some massage, I could somehow find an expression for the relevant norm here that is amenable to do Fourier analysis. But we are going to see the definition of this norm in the second part of the talk. And for the moment, what I want you to have in mind is that here we are going to change the infinity norm by another norm that is bigger or equal. And if we can say something about this norm, we can say something about the polynomials that are relevant for quantum computing, so we are going to focus on that. And somehow the picture that we have is that we had Aaronson-Ambainis conjecture, but we really care about the applications in quantum computing, so we don't really care about Aaronson-Ambainis conjecture itself. What we care is about the Fourier completely bounded version of Aaronson-Ambainis conjecture, which has this sequence of implications. So we know that Aaronson-Ambainis conjecture is stronger than the Aaronson-Ambainis conjecture for Fourier completely bounded polynomials. This is just because if you know that the Fourier completely bounded norm is at most 1, then in particular you know that the infinity norm is at most 1. The other way around is not true, so we have separations between the Fourier completely bounded norm and the infinity norm already for polynomials of degree 3. So for polynomials of degree 3, there is separations depending on the number of variables between these two norms. So this norm can be way bigger than the infinity norm, so having a bound on this norm can be, in principle, an advantage to prove this kind of results. This gives you more structure.
Yeah, I was just wondering, is there like a class of polynomials that separate these, or like what's the, what typically about your polynomial will mean that these norms are far away?
So yeah, I think like we know I guess that we know a few examples, but somehow I think that like an example that you can think of is when you take a polynomial of degree 3, like that is supported on all the monomials, all the possible degree 3 monomials, and you take random signs as coefficients, then with high probability or with some non-zero probability, one of these is going to be separated.
But isn't that handled by Montenaro's result?
What?
The example you just mentioned, is that kind of polynomial handled by Montenaro's result? It's like
No.
sines plus minus ones.
But Montenaro is block multilinear. So in Montanaro we had the extra structure that we divided all the variables in 3 blocks, like we talk about degree 3 multilinear forms, and in every block in every monomial there is one and only one variable of the block, so it's different.
Okay.
But we are not talking about the Aaronson-Ambainis conjecture in this case. What we are talking about is a separation between the Fourier completely bounded norm and infinity norm. That was a question about, right?
Yeah, but it would be funny if somehow this has one proof and then the other types of polynomials are covered by, but from this you can't recover, for the particular polynomials that have bounded FCB norm, does this imply, this still implies Aaronson and Ambainis. So you could potentially cover different parts of the class of all polynomials.
Yeah.
Proofs and...
Yeah, I hope, maybe you have to do something like that, like divide the problem in some cases and just use some machinery for every case. Yeah. But so somehow we have that Aaronson-Ambainis conjecture as stated originally. It implies Aaronson-Ambainis conjecture for Fourier completely bounded polynomials. The other way around is not necessarily true. And we still have that this conjecture that is weaker implies that quantum speedups need a structure. And somehow this is the picture that we know. So somehow this is a survey of what we know about Aaronson-Ambainis conjecture, what has been proven. And in the second half of the talk, what we are going to do is to define this Fourier completely bounded norm. We are going to see how you define this Boolean behavior for matrices, and we are going to prove a particular case of this Fourier completely bounded Aaronson-Ambainis conjecture, which is for polynomials that are homogeneous. So for this restricted class of polynomials, we can prove the Aaronson-Ambainis conjecture. I somehow argue that that is a particular case, but not that particular, because if you remember, this somehow even sounds a bit general compared to the particular cases that we knew about the Aaronson-Ambainis conjecture when we only had the infinity norm bound. So that's all for the first half. Thanks a lot.